All right, so in this video, we're going to talk about separable differential equations. And just as a reminder, we discussed in Calc 1 in its simplest terms, a differential equation is just an equation with derivatives in it. And to solve it, our job is to get rid of the derivatives. And many times, the easiest way is to actually integrate. So you take the antiderivative to come up with the original function, which is either the general solution or the particular solution, depending on if you're given an initial condition. So before we get into some actual differential equations to solve, particularly the separable kind, I do just want to kind of remind everybody real quick, if we have an equation like 2x plus 1 equals 5, if we solve this, we get x equals 2. Right? So in your earliest algebra classes, you were told to say, take this, x equals 2, and check it. To check it, you took this 2 and plugged it in for the x to make sure the left side and the right side work together to give you a true statement. Now we're going to check the solutions of some differential equations now to get started. So we're going to consider y prime equals y squared. Okay, so there's our differential equation. And we're going to check or verify that y equals negative 1 over x is a solution. Okay, now similar to what I showed you over here in blue, we would just take the part that we're needing or missing and plug it in. And we'll do the same thing here. I'm going to plug my y value in right there, but I also need a y prime on this side. So if I take my y prime, which I know is going to be a positive 1 over x squared, and then I substitute accordingly. I'm going to take my y prime right here and my y right here. This is now going to give me a 1 over x squared equals a negative 1 over x quantity squared. And so when I simplify this, it does in fact equal the same thing. So therefore, this function would be a solution of the given differential equation. Okay? So let's take a look at another one. We'll call this one letter B. If we take y equals negative 1 over x plus 3, we know that we'll need our y prime, and this is going to be a quotient rule. So we've got low derivative high minus the high times the derivative of the low over the low, which simplifies to 1 over x plus 3 squared. Okay? So once again, my y prime is now going to be this guy, and my y I'm going to take and substitute in with that. So in doing so, I'm going to have 1 over x plus 3 squared equals negative 1 over x plus 3 quantity squared, which is in fact the same thing. So we've just checked our answer, and we've also now shown that this is a solution to the differential equation. So if we take it one step further and generalize it, I think you guys will probably start seeing this all come together. If we know that this is a solution, and we know that this is a solution, well, what's the difference between these two things? It's this plus constant down here. So a general solution for this particular one would be y equals negative 1 over x plus c. And I would encourage you to go ahead, take a minute, pause the video, come up with y prime, and then take the y prime and set it equal to the y squared and check to see if it is also truly a solution to the differential equation. And you'll find out that it is. But anyway, that's how you'll check to see whether or not a solution or the solution given actually works into the original differential equation. All right, so now we're ready to actually look at some separable differential equations. And so when you guys actually take the course differential equations, you'll find out there are many different types, just like there are many different types of equations, right? There's quadratics, there's linears, there's rational, there's a million different types, and they all require different techniques. And it's the same thing with differential equations. There are different types that require different techniques. The first type that we're going to look at in this course is separable differential equations. And generally speaking, they're the simplest ones. So what we're going to do is we're actually going to separate all of the x's with all of the y's. And so if I divide by h of y and multiply by dx, so I'm moving this guy over here and I'm moving this guy over here. What that's going to leave me with then is a 1 over h of y dy equals g of x dx. At this point, when we want to solve it, because we have everything with the same variable on one side, we could just integrate both sides, the left side with respect to y and the right side with respect to x. And from there, we could solve for our general solution of the differential equation. Okay, so for this problem, we've got secant times dy dx equals e raised to the y plus sine of x. So that entire y plus sine of x is in the exponent of the exponential base e. So we're going to go ahead and separate, but before we separate, we need to use a little bit of algebra here. You can see that in this exponent, you have both a y and an x. So what we're going to do is actually come up with two separate exponentials. We're going to have our secant of x dy dx, and then we know how exponents work. We can take e to the y times e to the sine of x. Remember, if you're multiplying and the bases are the same, then you add the exponents. So this is in fact the same thing as this, but now we're going to have the ability to separate. I'm going to move my y over here and my x over here. Now to do this, I'm going to have a 1 over e to the y dy on the left, and on the right, I'm going to have this e to the sine of x, and then as I divide both sides by secant, I would have a secant in my denominator here, which when I flip around is going to give me my cosine. And I can't forget the dx that was also moved over as well. So this was just algebra and separating, going from here to here and separating the y's and the x's. At this point now, we can go ahead and integrate. So I integrate both sides. On the left, remember that left side, this is the same thing as e to the negative y. So when we integrate this, you could certainly use a u sub if you wanted to, but I have a feeling you've done enough of these by now to know that integral is just going to be a negative e to the negative y. If you're not seeing that, please pause the video, go off to the side, and integrate e to the negative y dy using a u sub. U would equal negative y, etc., etc. And we can also visualize it as if I take the derivative of this, I would also come up with this. But at this point, having done as much as you have, chances are you're able to come up with that pretty quickly. And then on the right, that is actually going to be a u sub. So over here on the right, I've got this e to the sine of x with cosine x dx. If I let my u equal sine of x, my du would equal cosine of x dx, so it's a perfect fit. So as I integrate that and finish it out, I would get e raised to the sine of x plus c. So here would be our general solution for the original separable differential equation. Some of these will end up a little nicer to where you can actually solve for y, for example. This is one where it's a little messier, so this would be an acceptable answer for this type of differential equation.